And thank you, Sune, for inviting me and organizing this conference. I think we should all thank Sune for organizing such a great conference. And
we should also thank the Hausdorff Institute.
Thank you. So everything was very great. Thank you for again inviting us. So this is about fusion systems. So we have representation rings for fusion systems. So we'll define a representation ring for a fusion system F, and we will relate this to what we call dimension functions. This all work came out of some questions about dimension functions. So the motivation actually comes from dimension functions. This is a joint work with Sune. Actually, we did most of this when I was in McMaster University on a sabbatical leave, and Sune came to visit us with when we were working with Ian Hamilton. So all three of us discussed, and at some point Ian came to Germany, and so we continued, and we proved. Was it? Ah, so yeah. So Sune stayed about a month, and eventually we were able to prove these results. So normally, actually, we start with fusion systems, but because this was a workshop on fusion systems, I want to make a difference and start with dimension functions. So I want to explain what a dimension function is, and then from there, we'll go to the fusion systems. So dimension functions are defined for homotopy G spheres. So throughout I will have G a finite group, and a G homotopy G sphere is going to be a GC double complex, and mostly I will have a finite one, but at this point we can say finite dimensional. We'll have GC double complex, and we'll want this to be homotopic to a sphere for some n, and we usually call these homotopy G spheres. Okay, and there is a theory by Smith. Oh, yeah, it's non-equivariant. Yeah. So on fixed points, we don't know what's going on. But the Smith theory tells us something about fixed point. For every P subgroup, P in G, if you take the P fixed points of this GC double complex, you get a mod P homology isomorphism to a sphere with some dimension NH, MP. And this MP is some integer bigger than equal to -1, and -1 always means that the fixed point set is empty. So we have some dimensions. So this gives a function. This is what we will be calling eventual dimension function. But and from a set to integers, where this set is the set of all prime power subgroups of the set of all subgroups G with prime power order. Okay. So it's union of all P subgroups, set of all P subgroups. Actually, we define, this is a little technical detail, but the dimension function of X as this n plus 1. We lift everything by 1 so that it's bigger or equal to 0. So now that's positive. And we call this dimension function. And call this dimension function. Of X. This one, adding 1 also helps you with giving an additive structure with the join. So now with the join of two homotopy spheres, their dimension functions are added up. So this, if I call this some sort of function, f, we notice that f satisfies a bunch of conditions. This list of conditions, some of it are obvious. For example, it's invariant under conjugation. So f of p is equals to f of q if p and q are G conjugate. And functions like this on the subgroups of a group is usually called superclass functions. So they look like class functions, but they're defined on the subgroups. So these are called superclass functions. Okay. And then,
So they're defined on subgroups?
yeah, exactly. If they're on the elements, it's class function. So for every p, f and p, of course this is now inside only this p, but the q fixed points are smaller than p fixed points, and they're all bigger than 0. And this is called monotone. So whenever you take a bigger subgroup, you have a smaller dimension. We have also some other conditions. Like if you have L, say H, where H is P group, these are in G, H is a P group, and H over L is CP cross CP. Also, say HI over L's all P subgroups, or subgroups of H over L of index P. If you have all these things, then you have a formula that holds. The difference between L and H is the sum of all the differences. Like this. So this is found by Borrer, that P fixed points, this for homotopy spheres, for P groups, the fixed points satisfy this. There's also other conditions for H over L isomorphic to CP, C4, or quaternions. We have modular relations. So for example, when H over L is CP, then the difference between these two is 0 mod P. So this is because when you have a P, so this P means odd. P odd. for odd primes, and you have an action, you have periods with cohomology CP with has 2, so to have such a thing, the difference has to be divisible by 2. For C4 you also have the same mod 2. For quaternions it becomes mod 4. So there's a little difference. But then, yeah. So you have to take another subgroup. But this is the only one I'm going to refer to, so I only wrote this one. Okay, so these 3, 4, actually 4 has long other things. These are called Borel-Smith conditions. And functions that satisfy these conditions are usually called Borel-Smith functions. So you may say, where do you find this? The easiest way to find Borel-Smith functions are to look at dimensions of representations. So if you take a real G representation, then you can define dimension V, defined by so at H or at P subgroups, this is the dimension of invariant subspace. And you can see that this is the same as the dimension of the corresponding unit sphere in this sense. So this is going to be same as dimension function of that unit sphere. This one satisfies Borel-Smith functions. So it's something that complete the algebraic. You can take a representation and check one by one if these are true. Okay. So you want to understand homotopy representations, homotopy G-spheres, and you found a bunch of conditions that has to hold by using complete topological techniques and like Borel's formula. And then you realize that these formulas, these conditions are very familiar. They hold for representations. So you can ask, then does all these homotopy G-spheres, or their dimension functions, do they all come from representations? And it turns out the answer to this is yes. And this is a theorem by Dotzer-Homlich. And it's yes only when G is a P group. So it has to be a P group. And if you take a Borel-Smith function, now it's defined on the subgroups of S. Borel-Smith function. Then you can realize it as the dimension function of a real representation. When it's F, then you can only do it virtually. There are real representations, real S representations, V and W, such that the dimension function is F. It's hard to write. I guess like Matthew, I'm used to writing with the soft pencil, so okay, so moreover, this is the part that is going to give us hard time. Moreover, if F is monotone, like I defined there, when f is monotone, then actual representation is possible. There is a real representation. Yeah, I take it out so that I can constantly state them as separately. Yeah. Yeah, condition 1 is part of it. So it's always a superclass function, yes. So condition 1 is always part of it. Okay. So real representation V is such that the dimension function is f. And the difference between this is huge. Like here you only realize it virtually. Here you actually realize it as a representation. You can see that difference is a problem if you want to actually get homotopy G-sphere. From this one, you can directly take the units sphere of this, and then you get a homotopy G-sphere. But from this one, you only get something virtual. So it's not clear how to use this one to get homotopy G-spheres. So this is a P-group theorem. And as you see, I use S there deliberately so that I can replace it with F eventually. So we will move into the fusion systems from there. But first, so the naive question you can ask, because I define dimension function on all subgroups of prime power order, and for a finite group G, you can ask, is Dotzer-Hamlich theorem holds for functions from P to Z? So does the Dotzer-Hamlich theorem hold for what are Smith functions from F to P? This is the all P subgroups, and for monotone, what are Smith functions when G is a finite group. So all these conditions I wrote before were only given for P groups. So at this point, we actually have no conditions of possible composite group actions. It's only given on P subgroup actions. So there is no reason for believing that this is actually true. And it turns out the answer is no. It can't be done, and there are very simple examples.
Sorry, in this case is P the fx prime subgroup?
This one is a P group. This one is all prime powers. So this is all prime order, all subgroups of prime power order. So all the primes. Yes, although we use P, still it's all primes together. You get all primes. I should say why we're interested in this kind of questions. So in transformation groups, group actions, there are lots of questions that you want to know if certain spaces admits certain type of actions. These actions are usually restricted by the isotropy. So you allow, you say action should be free, only isotropy is 1. Or you say action should be in such a way that the isotropy groups are rank 1. They don't have CP cross CP in them. So if you try to understand all finite groups that can act on a homotopy G-sphere with rank 1 isotropy, you need to understand if you can lift these kind of dimension functions. Because the isotropy is, you can see it from the dimension function. The values that you have no fixed point will have 0 value. So f of p is 0 if p doesn't fix any point. So the fixed point data, if something fixes a point or not, can be read from the dimension function. So by choosing right dimension functions at the beginning, if you can realize them, then you're constructing actions with restricted isotropy. So these kind of questions are important. Okay, so there's a very simple example. You can take C5, semi-direct C4, where C4 acts on the units of C5 by rotating everything. And this thing has, you can see that real representations if you restrict it to C5, it has to respect the fusion coming from C4. So you can only have augmentation ideal, or you can have the trivial one. So this tells us that the dimension of V minus dimension V by C5, this actually is divisible by 4. But I have no Borel-Smith condition that tells me this. So Borel-Smith condition gives only that it's divisible by 2. So by this relation for a CP action, I only have divisible by 2. So I miss some dimension functions. I can't realize them. Unless I multiply with 2, then I can. But given a dimension function satisfy Borel-Smith conditions, it cannot be dim V. Okay. So this shows that there's a problem, and this problem actually easily fixed. This C5, C4 situation occurs because you have actions on this kind of CP sections, and you have a coprime Q group acting on this, and you can easily add a relation. So if you add a relation to this list, maybe as 5 or as a star, you can fix that problem. And this is done by Stefan Bauer. Actually, he added this relation in 1989. So I will write this relation, and then I'll tell you what he proved. So if you have 2 primes, and we want them different, I guess, for this. And if we have 2 subgroups normal in each other, and of course we want this to be so that L is normal in there. So like this, such that so we want H to be a P group to avoid bad things, and H over L is CP, and let's say then we could say HL minus FH is 0 mod Q to the R minus L if M over H is a CQ to the R acting on H over L. So acting on H but fixing L, so H over L with kernel Q to the L, kernel of order. Okay. So the faithful part, the order of the faithful action on CP should divide the difference. So when you have a this situation, this is exactly the situation you have with C5, C4, because C4 acts faithfully on C5, and then there Q is 2, but faithful action means then L is 1, this Q to the L is 1, so this thing becomes 4, and the difference is divisible by 4. Right? Any questions? Maybe too much dimension functions? I hope it's not. I will come to the fusion. I mean, I'm hoping to skip the proofs anyway, so I think I have a lot of time. If I go to the proofs, and that's, I think, more difficult to follow. So this one is, so the theorem Bauer proves is that Dotzer-Hamlick theorem holds for finite groups, for maps P to Z, but only the first part holds under this condition. So if F is a map, again defined under P prime power order subgroups, is a monotone Borel-Smith functions, satisfying star. Again, in this field, there's 7-8 different definitions of Borel-Smith functions in different conditions. Some people put this star into the Borel-Smith set, but I think it's too much. I know it's kind of, but Stefan Bauer actually adds it to the list and says Borel-Smith function. But oh, sorry, this is not a monotone. So the monotone version, this doesn't exist as a satisfying star. Then there exists a virtual representation. So real representations, V and W, such that the difference of dimension functions realizes F. And there is no monotone version for this. Actually, we have an example to show that why it doesn't. There is no monotone version. I should use the water, but to worry that it's going to take longer, so I'm just going to do this. So there is no monotone version. Huh? So very easy example, which we had to cook up, but not very difficult to see. For S3, where you have C3 and C2 and 1 is there. So these are the conjugates of it, of course. This is the family of P subgroups. So for this one, you can write a monotone function which has 2, 2, 0. Of course, on the conjugates, you have the same value. So this F is a dimension function of 1 minus 1. So this is the trivial. This is the twisting one, plus a two-dimensional representation. So this realized by virtual representation, but there is no actual representation that realizes this for any. So this is a very simple example, but it's really saved a lot of agony for us. We understood immediately that one has to do some other things if you want to. So again, from the transformation group or group action perspective, you want to realize dimension functions, not virtually. So you want to realize them, but not necessarily as a representation, because we're not doing linear representation theory, we're doing topology. So not having representation is bad, but it's expected and not so bad. So you can still ask yourself, given a monotone dimension function satisfying all these conditions, this actually satisfies, so this satisfies all the conditions. Whereas Smith function conditions, it also satisfies the Staffen-Bauer's condition. It's a very simple dimension function. It satisfies everything, but it's not realizable by a representation. So you can ask yourself, this is the question, can I still do this by G homotopy representations? Can I still find a finite GC complex? So given a monotone Borel-Smith function satisfying this condition, does there exist X? So does there exist a G homotopy G sphere such that the dimension function for X is exactly F? And the answer to this, we don't know. This is actually still open question. And this is related to something Jesper did with Jeff Smith. And they asked similar question for algebraic homotopy G spheres on the level of chain complexes. This is a question that was asked by Jesper and Jeff Smith. There you don't want necessarily actual G sphere, but you want a chain complex over the orbit category, which is fine.
G spheres, but just then it should be p-adic spheres, and then you don't use the condition stop.
And you focus on 1 prime, right? So you also have only 1 prime.
Right, yeah.
So these kind of questions have been around.
How about, okay, first, in this one you realize, this particular one you realize?
Yes, this is realized. We actually realized this with our work with Ian. So we constructed actions of certain finite groups with rank 1 isotropy, and this is realizable.
And if you add the condition, I'm just curious, it's clear that if F1 is met C2, then it can't be realized by a representation.
Yes, so the problem is not the monotone. The problem with this is that this is the one that all these values are non-zero, 2, and the subgroup generated by this is not a 2 group.
Yeah, exactly. That's what I'm asking. Can you, but if F1 is strictly greater than C2, is it always realized?
I don't. I don't think you can realize it with this non-zero, and this is non-zero. This is 0 at the same time. So I mean the problem is this also. So if you increase this, you have to increase this too. But yeah, cases I haven't, of course, told about every. But this was one of the examples in our paper with Ian, because there is a difference between a G homotopy sphere and a homotopy G representation. So representation, homotopy representations have been studied by Tom Dick, and one of the conditions they have is that on fixed point sets, it's not only a sphere, but it's the dimension, geometric dimension, matches the homology dimension. So if you have that extra condition, it's called homotopy representation. And we actually use this example to say there's no homotopy representation in this case. And same problem occurs there. And you can find the homotopy G sphere, but you can't find the homotopy representation. So these things you built will have cells above the homology dimension. and you can avoid it. That's the big difference. And any representation, this is homotopy representation. Already, you have no cells above the homology dimension. If you take the fixed points, it's there. There's no cells. So that's why you can't get a homotopy representation, or you can't get an actual representation. Okay, so I'm a little running late now, so how about I speed up on this note? But this is an open problem, and it's something that will get tangled with some other open problems we have about fusion systems. So we have actually a conjecture about fusion systems where is relevant for this open problem. Okay, so what we prove, maybe I state the theorem now. This is with Sune. So I call this theorem 1, but it's actually the last theorem in our paper. We prove that this is, the answer to this question is yes, if you're allowed to multiply f with some number. Okay, so maybe given a monotone, and you no longer need the condition star because you're allowed to multiply with a number. So monotone Borel-Smith function f defined on P subgroups of a finite group G. There exists an N and a finite GCW complex X homotopy equivalent to some sphere with, this is also nice, with isotropy in P. So the construction tells us the isotropy is already a prime power subgroup such that the dimension function of this X realizes n times f. So up to multiplication with a scalar, you're able to answer this question correctly. And the isotope being in P is good because you have no composite isotropy. It has some more control over the GCW complex. And this Borel-Smith function, only 3 is enough. Only one of those, only the Borel condition actually is necessary. Only the sum condition is necessary. So you can. Yeah, exactly. Yeah. So none of the mod relations matter. Only the sum formula. And you can obtain such a thing. And honestly, I mean, if again going back to, if you want to construct group action with certain isotropy, you only care if the values are 0 or not. So multiplying with the integer was not a problem. We really, I mean, from the perspective of constructing actions with values 0 on certain subgroups, multiplying the dimension function with the integer doesn't hurt it. So this is actually as good as, I mean, this is what you were looking for to start with. That's actually, but it's still interesting to be able to answer the other question. That original one. Okay, so how you prove anything like this? You prove this using representation theory for fusion systems. So representations. We fusion systems. So this is my second part. Just to make the connection, so we okay. So let me give you a definition, and then I'll state the theorem and say how this theorem gives theorem 1. So let F be a fusion system on a P group S. A representation, and so we fix some coefficient ring. Maybe I should say this here. Some coefficient ring as a subring of complex numbers. And we just actually care only these 3 cases. Subfield. So we only, I mean, K is either R, C, or Q. So K linear S representation, V is called F stable.
You mean a ring or subfield?
Subfield, I guess. I hesitated that, but I just, yes, we just wanted the field. Yeah. But everything will be subfield. No? So it will be okay. I just want this 3, but I think it's subfield. Called F stable if for every morphism in F, if you restrict this representation to P using since Bernard is here, maybe I should say a couple of things about what the fusion system is. But this is, we by now, everyone knows this. So this is morphism in the fusion system. So we want this to be true for every morphism in the fusion system. So this is basically saying that if you take an element in V and multiply with something in P, you get the same effect that doing it by first applying this morphism phi and then multiplying with the image of that. So these representations are stable under the morphisms of the fusion system. And when F is the fusion system of the group, this corresponds to saying that conjugate elements have same values on the character table. And so F-stable representations comes up because to get such a GCW complex, we have a method we proved in a paper by Ian, which says that such a GCW complex is possible to construct if you can find F-stable representations for every pseudo-P subgroup inside here. Okay, so this is basically the theorem. This is what gives us what we want. So given a fusion system, and for our Smith function, F stable under F, this meaning F and also respects the values of P and Q if they are conjugate in F. There exists and n, and a real representation, and f-stable real representation V, such that the dimension function of V is equal to n times f. So if you are given a Borel-Smith function which is stable and monotone, of course, let's start with a monotone, stable under f, that normally f conjugate elements don't have to be equal. This is Borel-Smith functions on the subgroups of S. If you have a Borel-Smith function which respects the f conjugation, then for some n you can find a f-stable real representation V, so that its dimension function is n times f. So this is at 1 prime p. So on a p group S. So it's a theorem on 1 prime p defined on the how they apply to this situation where this starts with G finite group. So given a finite group, this is all prime power order subgroups. So for each of the 0p subgroups, you apply this theorem, because when you restrict this Borel-Smith function to each of the 0p subgroups, you get a monotone Borel-Smith functions defined on the 0p subgroup, which respects the fusion, which respects the conjugations coming from G. So this condition will be satisfied. And then this theorem says for every 0p subgroup in this family, you have a representation which is f-stable. So the representation respects the conjugations of G. And how do you get something G action out of it? That's a theorem. This is a theorem by Ian Ambleton and me. And we proved that you can actually, there's a method for constructing such an action. You can construct these actions by using G equivariant fibrations over some base space and doing fiber joins. It's a very topological construction. And because it raises the dimension of the representation, you multiply your representation. So this n is not necessarily equal to that n. Okay, so this becomes much bigger. You even have to multiply more n's. But eventually you can get from theorem 2 to theorem 1 by just using something already exists. So it brings us to how to prove theorem 2. And this is what this talk is about, as usual. Okay, so it's only defined in terms of fusion systems, and I have 10 minutes, so I should be able to. Everyone knows fusion systems, so. I want it saturated, I guess. Where is it? Yeah, saturated. As you see, I mean, our main application will be actually a fusion system coming from a finite group. So we don't know really any of this is interesting in the exotic case. But for us, the main motivation is finite groups. So you can even assume that's a fusion system. So what we do, so the idea or the pieces for the proof, you first start with analyzing this dimension function using a representation ring and ring of Borel-Smith functions. So we have representation ring defined over a field for a P group. You can extend it to fusion systems. So if again a fusion system saturated so this is I think it exists in the literature, maybe we weren't sure, but this is something you define easily. as the f-stable elements in the usual representation ring for S, which is stable. In the fusion system. And we proved it via lemma. This is a lemma, but it's not that hard. You can prove that this is same as the Grothending ring of monoid of the f-stable representation. So this is Grothending ring of the semi-ring. We can care about the ring structure too if you want. Of f-stable k-linear representations. So there's a small thing to prove here, but it's true. And you can use this. You can also define f-stable Borel-Smith functions. So you can define this as all the Borel-Smith functions which is f-stable. And this is a group, abelian group. And you can define a dimension map from this ring. Now I switch to real representations because this is where we care the most. And you can take a representation and take it to a function that takes the fixed point set, invariant sub representation. So this is the dimension function which is going to be f-stable because v that you start with is going to be f-stable. Although Sejong was saying that we don't need this lemma, but anyway, the lemma tells you that this is going to be well defined. So you have this, and what we do is we prove that this tells us the dimension function is surjective if you p-localize. It's surjective. And we actually prove this using a more general argument that any short exact sequence of biset functors, you can define the fusion system version of them by taking the f-invariant, the f-stable subrings, subgroups. And then when you p-localize, it corresponds to cutting it with characteristic idempotent for the fusion system. So it's a very easy argument. You can show that when you define as a f-stable on a biset functor, and then p-localization is just the cut. So these are all cut by the characteristic idempotent of the same thing for S. So this allows you to move all the exact sequences into p-local exact sequences.
But also localized, right?
Yeah, exactly. Everything is localized. So p-locally, you can move all your exact sequences from the S to F. This is what we find out. And this is surjective by Doster-Hamlich. So idea, this is surjective for P groups by Doster-Hamlich. This is exactly what they prove, right? And then you do this cutting with idempotent, and exact sequences goes to exact sequences, so surjective maps goes to surjective maps. So you have this nice observation. What we did, we defined, so On the P group case, we needed this Stefan-Bauer's condition to make surjectivity in integral coefficients. And in the fusion world, the Bauer's condition still exists. It exists in terms of automorphisms of P groups in the fusion system. So you can define a subgroup of the Borel-Smith functions as the ones that satisfy a version of Bauer's condition. As the subgroup of Borel-Smith functions satisfying a version of Bauer's condition. It's very easy. I mean, if you have automorphism of CP inside the alt F, if its order is M on the quotient H over L, then the difference has to be divisible by M. It's just very easy to generalize that. And then, so is the Bauer's condition added to CB? Do you get a Bauer's theorem? And we showed that yes. So our theorem, actually one of the main theorems is Theorem 3. We'll say that with the Bauer's condition, dimension function is surjective integrally. So so if you add the Bauer's condition in the fusion setting, you suddenly have a surjective map. So this is Theorem 3. So the dimension functions, the dimension homomorphism. So we go from re-representation ring fusion system to the Borel-Smith satisfying the Bauer's condition. It's surjective. So Bauer's condition, or things Bauer proved for finite groups, holds for abstract fusion systems. And you don't need to assume F is a fusion system of a group. It's just true for arbitrary fusion system. And that's possible to do it. Now, with one word, let me finish what we do. So I stated 3 theorems. One of them I just erased, but the theorem I erased was about GCW complexes, homotopy equal to a sphere, and it only needed this theorem 2. And now we prove this theorem 3, which is for fusion systems, saying that Bauer condition guarantees a representation. So this means this is lifted by a virtual representation. So this is not a monotone result. And a version of this for monotone F doesn't exist. We discussed this already. So how do we prove this without the monotone version? We use the monotone version of Dotzer-Hamlich. So Dotzer-Hamlich theorem says when you have a monotone function, this monotone function leads to actual representation, not just a virtual one. So that actual one doesn't have to be F stable though. It's a representation of S. So what you do by multiplying with some number, F, you can guarantee that the representation that comes from Dotzer-Hamlich is actually comes from a rational representation. So you can average your Galois conjugate average of your real representation, multiply with an integer if you need, and assume that it's rational. But when it's rational, dimension function is injective. So for rational numbers, the isomorphism type is detected by fixed points by cyclic subgroups. Rational representations we have this theorem. They're isomorphic if and only if for every cyclic subgroup inside G, the fixed points are same. So this means dimension function detects if they're same. Okay.
Why is that actually true?
This one is true.
Yeah, why is that?
This tells us that the dimension function, remember this was the dimensions of the fixed point set. Why this is true?
Yeah, why is that?
It's because rational representations, you have Galois conjugates, you can't be different on the different elements of the cyclic subgroup, so if you sum it up, I don't know, what else? Yeah, that's another thing.
So it has to come from a permutation.
Anyway, so this becomes crucial to check that the Dosser-Hamdic representation is actually stable, F stable or not, because then the F stability is checked on the dimension functions, and it's already stable on the dimension function. We already know that F is F stable, so it becomes F stable because of that. But you have to multiply with numbers, and you take Galois conjugates. So the lots of multiplication is involved. So this n is not a joke. I mean, you have to put an n there, otherwise the argument doesn't work. But it's not a very deep, very difficult thing to prove Theorem 2 once you have these things. Okay, that's all. Thank you. Yeah,
We don't have a complex sample to say that the monotone version of theorem 3 isn't true. So you could ask if we have a Gaussian function with the extra condition that's monotone, does it lead to an stable representation? We actually don't know.
so this,
We've checked it actually holds.
so given a monotone F, does there exist an F-stable representation such that its dimension function is equal to F? And this is an open problem, a conjecture question. So you want to know if and this is monotone, it's liftable or not. So that finite group example tells you can't do it for finite groups, but on fusion systems it's still open. We don't know if it's possible or not.
So you would need. So there's a counterexample.
The S3 counterexample doesn't work on this because it's only one CRP subgroup. You don't have the whole group. So it becomes just C2, and C2 you can always realize. So, it's good. Good point.
Other questions? So,
No, thank you.